One of the real sticking points in getting AI truly useful in medical imaging is just the sheer amount of detailed work needed up front.
Oh, absolutely. The training data problem.
Exactly. Imagine needing to draw like a perfect outline around every tiny anomaly in thousands of scans.
That's what experts have to do now, basically. It's slow, painstaking.
And expensive.
Mhm.
It costs a fortune and takes
Mhm.
forever. It really creates a major bottleneck.
Definitely.
But what if we could kind of get around that really intensive labeling?
That's the goal, right? Find smarter ways.
Well, today we're doing a deep dive into some fascinating research that offers a really clever new approach to this exact problem. It could potentially unlock a much faster path to sophisticated medical AI.
Sounds promising.
Yeah, I
Yeah.
think prepare for some serious aha moments as we figure out how different AI techniques can, team up in unexpected and frankly brilliant ways.
Okay, I'm intrigued. And the paper title itself gives a clue, doesn't it? From gaze to insight. Bridging human visual attention and vision language model for weakly supervised medical image segmentation.
Right. It points straight at the core idea.
It suggests using two, let's say, less precise types of information to get really detailed results in the end.
So our mission for this deep dive is basically to break down how this framework works
What makes it innovative?
and why it could be a really big deal for medical AI development.
Mm.
And we'll try to do it without getting, totally bogged down in the super technical jargon.
Sounds like a plan. Let's get into it.
Okay, so this central idea, the researchers had this, really smart thought.
Hmm.
What if you combined where an expert looked with why that specific region matters? Like think about a top radiologist looking at a scan. Their eyes just naturally go to the important bits. That's the where.
The gaze data.
Exactly. And then you have these incredible vision language models, VLMs, that can actually describe what's in an image.
Right, they can generate text saying, lesions, smooth edges, upper left quadrant, things like that.
But, and this is key, neither of those pieces of information is like perfect on its own, is it?
That's a really good way to put it. The gaze data tells you what caught the eye, but it can be a bit scattered, maybe noisy.
Yeah.
Not every single place the eye lands is crucial, and it often gives you just a rough area, not a sharp, exact boundary.
Okay.
And then the VLMs, they give you that crucial semantic content, the description, but they aren't always pinpoint accurate at the pixel level.
Especially medical images, I imagine.
Exactly. Things are subtle. So a VLM might not nail the exact shape or boundary, or sometimes they can even hallucinate details that aren't quite right.
It's almost like trying to find a specific shop in a really busy area. The gaze data is like someone vaguely pointing, it's kind of over there.
Yeah, good analogy.
And the VLM gives you a detailed description, small bookstore, green awning, but you still don't know exactly which building it is on the street.
Precisely. So the real magic here, the innovation, is how they figured out how to weave those two imperfect clues together effectively.
Okay, so how do they do it? What's the mechanism?
They use what's called a teacher-student framework. This is actually a pretty common technique in AI.
Right, where one model teaches another.
Exactly. The teacher model learns first, gets a good understanding, and then it guides the learning process of a second model, the student. In this research, it's a really clever way to leverage the specific strengths of both the gaze data and that VLM information.
Okay, let's unpack that. The teacher model first. How does it learn from these less than perfect inputs?
So the teacher starts with what they call sparse pseudomasks. You can think of these as being built from the most reliable bits of the expert's gaze.
The high confidence points, where they really looked hard.
Pretty much, yeah. The spots where it's highly likely they were focusing on something significant. But because these are just points, or maybe small areas, they don't give you the full shape of, say, a lesion.
Right, still incomplete.
That's where the VLM comes in crucially. The researchers used a very specific, structured prompting method. They didn't just ask the VLM, describe this image.
Ah, okay. More targeted.
Much more. They prompted it to describe specific morphological characteristics, the lesion's shape, its size, location, boundary type, things like that. They show examples in the paper like structured outputs, location, upper left, boundary clear, characteristics, dot smooth.
Got it. So it's like filling in a form about the lesion using the VLM's understanding. That provides much more concrete information for the AI.
Exactly right. It guides the AI much more effectively than just a general caption.
Okay, so the teacher has these sparse gaze points and these structured text descriptions. How does it blend them?
It uses something called multi-scale text vision fusion. Basically, it integrates these text clues with the visual features it's extracting from the image at different levels of detail.
So like looking at the image zoomed in and zoomed out and connecting the text description to what it sees at each level.
That's a good way to think about it, yeah. It helps the model build a strong link between the visual patterns and the semantic descriptions. And because that initial gaze information is sparse, it only covers parts of the image. The teacher model uses a special kind of loss
A
function.
way of measuring error.
Right, it's called partially cross-entropy loss. It essentially tells the model to focus its learning primarily on those areas where it does have that reliable gaze information.
Okay, that makes sense. Focus where you have good, if sparse, ground truth. So the teacher gets this initial refined understanding by blending the where from gaze and the why from text. Now, how does it pass this knowledge on? How does the student learn?
Okay, so the student model learns from something different. Comprehensive pseudomasks. These are derived from a broader set of gaze data.
Including the list certain points, maybe some noise.
Exactly. It covers more of the potential lesion area, but it's inherently less reliable, potentially noisier than the sparse set the teacher used. The teacher then guides the student through knowledge distillation.
Right, transferring the knowledge.
And they use a few really interesting techniques for this. First, there's feature-level alignment. They use a specific method called angular feature consistency loss, or AFC.
Okay, what does that do?
Think of it as encouraging the student model's internal representation of the image, features how it sees and understands the visual patterns to become similar to the teacher's more refined understanding.
So the student learns to see,
Right.
like the teacher.
In a way, yes, to interpret the important visual cues similarly. Then they use something called confidence-aware weighted consistency loss, or CWC.
Confidence aware.
Yeah. This technique focuses the student's learning on the parts of the image where both the teacher and the student are making predictions with high confidence.
So areas of agreement reinforce the learning.
Precisely. By emphasizing these high confidence agreement areas, they strengthen the learning where they're most likely correct. The paper even mentions specific thresholds they used, like 0.8 for high confidence positive areas and 0.2 for high confidence negative areas. And finally, the student also uses a more standard comprehensive cross-entropy loss, but this time over that broader, potentially noisier set of gaze masks.
Right, so it's learning from the full gaze data, but with this strong guidance from the teacher, especially focusing on where they both agree strongly. But what about the noise? What about those gaze points that might just be wrong?
This is where I think one of the coolest innovations comes in. It's called disagreement-aware random masking, or DARM.
Disagreement-aware random masking. Okay,
Yeah.
sounds interesting.
What it does is it looks for areas where the teacher and the student are making significantly different predictions where they disagree, and then it randomly hides or masks parts of the input image in those disagreement regions.
Whoa, okay. Why do that?
By hiding those contentious parts, it prevents the student from just overfitting to potentially incorrect gaze data points in those zones. It forces the student to rely more on the surrounding context and the knowledge it's already distilled from the teacher to figure out what's going on there.
That's really clever. It's like saying, okay, you two can't agree on this spot, so student, ignore it for a moment and use everything else you know to make the call.
Exactly. And it seems to work really well. They show in one of their tables, Table 7, that turning off DARM causes a significant drop in performance.
Wow, so that really highlights how crucial it is for dealing with the inherent noise in the broader gaze data.
Definitely.
Okay, let me try and summarize this. Teacher model uses sparse but reliable gaze points, enhances them with detailed text descriptions from a VLM using structured prompts and multi-scale fusion. Student model learns from broader, potentially noisy gaze data, but gets guided by the teacher through feature alignment and confidence-aware consistency, and uses this clever DARM technique to handle areas where the teacher and student disagree.
That's a great summary. You've got it. And that really leads us to the core contributions of this research.
Right, what are the big takeaways?
Well, first, as far as they know, this is the first framework to really combine expert gaze and VLMs for medical image segmentation in this way.
So true novelty there.
Yes. Second, it's the development of this specific teacher-student architecture tailored precisely for integrating these two types of weak supervision.
The structure itself is an innovation.
And third, it's those three key technical pieces we just discussed. The feature-level alignment, AFC, the confidence-aware consistency, CWC, and that disagreement-aware random masking, DARM.
Got it. Innovations in approach, architecture, and specific techniques. And I assume the results back this up.
You really do. They tested it thoroughly on 3 different medical imaging datasets, which is important to show generalizability.
Okay, what were they?
First, Quasir-Seg. That's for segmenting polyps in endoscopic images, like from a colonoscopy.
Right.
Here, they achieved a DICE score, which is a common metric for segmentation accuracy of 80.78%.
How does that compare?
Well, they point out it's a solid 3 to 5 percentage point improvement over methods that only use gaze data. And interestingly, it was even better than some methods using other forms of weak supervision like bounding boxes or simple scribbles. And they specifically mention it works well for tricky cases, like small or irregularly shaped polyps. You can actually see some visual examples in Figure 3 of the paper, which look quite impressive.
Okay, that's a significant bump, especially if it helps with the harder cases.
Yeah.
What other data sets?
Next was the NCI-ISBI dataset. This involves MRI scans for prostate segmentation.
Okay, different imaging modality, different anatomy.
Exactly. And here they reached a DICE score of 80.53%. Again, about 3 to 5 points better than the gaze-only baseline methods.
Similar improvement level.
Yes, but what's perhaps even more striking here is the efficiency gain they highlighted.
The time saving.
Huge time saving. They compared about 2.2 hours needed for collecting the gaze data versus an estimated 18 hours for getting full, pixel-perfect manual annotations for the same data set.
Wow, 2.2 hours versus 18 hours. That's nearly an order of magnitude faster.
It's enormous, and they achieved accuracy that's near the state-of-the-art obtained with full supervision.
That really underscores the practical value, doesn't it? Making high-quality AI feasible without that massive annotation burden.
Absolutely. And the third data set was ISIC, which is for segmenting skin lesions from dermoscopy images.
Skin cancer detection territory.
Right. Here they got a DICE score of 84.22%. And they noted that it outperformed other gaze-based methods not just on DICE, but on several other metrics too, like MIOU, HD95, and ASD, which basically measure different aspects of segmentation quality, including how well the boundaries are delineated.
So consistently strong performance across different types of medical images and tasks. Better accuracy than gaze only, approaching fully supervised results, but with way less annotation effort.
That's the headline, yes. And it also seems to offer better interpretability because you can potentially align the gaze points, the text descriptions, and the model's final prediction. Figure 3 hints at this too.
That makes sense. It connects the human expert's focus to the AI's reasoning. Now, you mentioned they did ablation studies to sort of prove why it works.
Yes, exactly. Ablation studies are crucial in AI research. They systematically remove or change components of the proposed system to see how performance is affected. It helps validate that each piece is actually contributing positively.
Right, like taking the engine apart to see what each part does. So what do they find?
Well, they confirmed several things we've touched on. For instance, the way they prompted the VLM. Those structured prompts significantly impacted performance compared to simpler prompts.
So the quality of the Y signal matters a lot.
Definitely. They also showed their multi-scale text vision fusion worked better than just, say, concatenating the text features at the end.
The integration method was important.
Yes. And critically, in the student model, they showed that both the angular feature consistency, AFC for feature alignment, and the confidence-aware consistency, CWC, were crucial. Removing either one hurt performance.
So both guidance mechanisms are pulling their weight.
Correct. And, as we discussed earlier, disabling the disagreement-aware random masking, DARM, led to a significant performance drop, confirming its vital role in handling that noisy, comprehensive gaze data.
Right. Proving the value of that specific innovation.
They also experimented with things like how deeply they integrated the text and vision cues in the teacher model, finding more integration helped, and they showed their chosen confidence thresholds for the CWC loss seemed pretty well calibrated.
Okay, so these studies really nail down that the specific design choices they made, the teacher-student setup, the fusion technique, the consistency losses, the DARM, all meaningfully contribute to the final result. It's not just one lucky trick.
Precisely. It's a well-thought-out system where the parts work together effectively.
So bringing it all together, why does this matter for someone trying to, keep up with AI? What's the big picture significance?
Well, I think for the learner, it demonstrates a really clever and practical way to tackle that fundamental annotation bottleneck in medical AI.
Which we know is a huge hurdle.
A massive one. It also showcases the power of combining different AI paradigms, sophisticated vision language models, alongside more traditional segmentation networks, and integrating them with a unique form of human input, the gaze data.
Showing that synergy between different AI approaches can be really powerful.
Exactly. And it offers a potential pathway to developing medical AI systems more efficiently, which could mean they get deployed more widely and potentially help more people sooner.
Faster development, potentially broader impact.
And fundamentally, it highlights the importance of understanding not just what AI can do, but how it works specifically, how it can leverage different, sometimes imperfect, sources of information in creative ways.
So the key takeaway really seems to be that this smart integration of human visual attention, the where, and AI-generated semantic context, the why,
Hmm.
offers a really promising route forward. We can potentially get accurate medical image segmentation with dramatically less annotation effort.
That's the core message. And it prompts a really interesting thought, doesn't it?
Oh, what's that?
Well, think about where else this kind of approach might work. Are there other domains outside of medicine where you have expert attention data, maybe eye tracking from pilots or designers or analysts, but getting detailed labels is just as hard?
Hmm, that's a great point. What other kinds of where and why signals could be combined? Manufacturing inspection, quality control, security analysis.
Potentially, yeah. It makes you consider the broader applicability of combining human perceptual signals with AI's analytical capabilities.
It definitely sparks some ideas. And for listeners who really want to get into the nitty-gritty, you mentioned the code is available.
Yes, the researchers included a GitHub link in the paper's abstract, which is great for transparency and for others looking to build on this work.
Fantastic. Well, this has been a really insightful look at a clever piece of research. It's a great example of the continuous advancements in AI and, its real potential to transform fields like medical diagnostics.
Agreed. Really promising work.